Welcome to Math with Professor V. In this video, I'll be solving a Calculus 2 exam that has to do with the unit on sequences and series. This is actually an old exam that I gave to my class back in fall 2019, and I had a request to solve another exam on sequences and series, and I pulled up an older one because I used to give longer tests than I do now. And so this one just has more problems for you guys to see and practice with. If you need more problems after this, I have so many video lectures on all things sequences and series, so I'll link the playlist in the description and at the end of this video. Okay, starting off, let's talk about sequences. First problem asks us to find the limit of the sequence if it converges, otherwise indicate divergence. So remember, for a sequence, not a series, a sequence, if the limit as n approaches infinity of an is some finite number L, then we say the sequence converges. And then if the limit as n approaches infinity of a sub n is either positive infinity, negative infinity, or doesn't exist, then we say the sequence diverges, okay? So not the same criteria as a series. All right, so find the limit of the sequence if it converges, otherwise indicate divergence. I'm noticing right here, this is an alternating series because we have that -1 to the n. So all the odd terms are going to be negative, all the even terms are going to be positive. It's difficult to take a limit when you have that alternating term in there. So what we're going to do is make use of a theorem that you should have covered in this first section. And the theorem states the following. If the limit as n approaches infinity of the absolute value of an, the absolute value of the terms, is 0, then that implies that the limit as n approaches infinity of a sub n without the absolute value is 0. And that should make sense because if you make all the terms positive and they approach 0, then whether or not they're positive or negative, they're still shrinking. They're still approaching 0 in magnitude. So let's apply that theorem here and see if we can make a conclusion now. So let's look at what is the limit as n approaches infinity of the absolute value of an, so absolute value of -1 to the n times 5 over n. Now when I take the absolute value, this term just goes away, right? Because it's going to become +1 to the n, which is just 1, so I don't even need to write it. So then we've got the limit, n goes to infinity. N isn't going to be negative, so I don't even need to keep writing absolute value. I could just put 5 over n. And then we know, okay, constant over a denominator getting very, very big, that's 0. So let's make sure we answer the question, find the limit of the sequence if it converges. We did, otherwise indicate divergence. I would just say, out of paranoia, I would just write down it's convergent. You probably don't have to because we found the limit, so that implies it's convergent, but just to be safe. Okay, how was that one? So don't forget that theorem. It doesn't have a name, but it's pretty much in every single textbook. You should learn it when you're covering sequences. All right, so let's look at another sequence. Again, this one's alternating. We know that because we see this -1 to the n term. So let's try the same approach that we did last time. Let's look at the limit as n approaches infinity of the absolute value of -1 to the n times 1 minus 8 over n. And just like before, when we take the absolute value of -1 to the n, it's going to make it +1 to the n, which is just 1. So we have the limit as n goes to infinity, absolute value, just 1 minus 8 over n left. Okay. As n gets really, really large, 8 over n is going to approach 0. And then all we're going to be left with is absolute value of 1 minus 0, which is just 1. Can I use my theorem? No. My theorem says if the limit of the absolute value is 0, then the original sequence without the absolute value approaches 0. This is not 0. This is not 0. So what can I conclude from here? Well, I want you to notice that anytime the absolute value of the terms approaches a non-zero number, that means the odd terms versus the even terms have different limits. If you were to list out several, you would see that. So all of the odd terms, what do I mean by odd terms? Like a sub 1, a sub 3, a sub 5, etc. Because they all will have odd values of n, they're going to be negative. So negative 1 to some odd number is going to be negative. And then as n gets larger, this quantity will approach 1, but all of these terms will actually be approaching negative 1. They approach negative 1. The even terms, a2, a4, a6, etc., they're going to have negative 1 raised to some even number. So that's going to make them all positive. And then as n gets large, this quantity again approaches 1. So all of the even terms will approach positive 1. So the limit of this sequence doesn't exist because the odd terms are approaching negative 1 and the even terms are approaching positive 1. They need to go to the same place. And later, if you study more math, if you decide you want to be a math major, you'll learn that a convergent sequence has to have every subsequence converge to the same limit. So basically, you can't have a subsequence of odd terms or a subsequence of even terms going to different places if your overall sequence is convergent. That's a big no-no. So then from here, we can just conclude, okay, this means the limit as n approaches infinity of negative 1 to the n times 1 minus 8 over n does not exist. So then the sequence is divergent. Okay, how was that? Hopefully that makes sense. And, you know, sequences can be tricky, especially because you only cover them in a little bit part of the unit, and then later on you focus on infinite series so much more. So if you need more review on sequences, I have plenty of videos. I'll link them in the description. Okay, next, determine if the sequence is monotonic and if it's bounded. If it is bounded, justify by finding the upper and lower bounds. Okay, so to prove a sequence is monotonic, you have a few options. You can use an inequality and compare a sub n plus 1 versus a sub n. If you can show one's always bigger or smaller than the other, then you can show it's monotonic. Another thing you could do is look at the ratio a sub n plus 1 over a sub n, or the other order. If you can show that's always greater or less than 1, compared to 1. You can do something like that. You could look at the difference. You could do a sub n plus 1 minus a sub n and then show that it's less than or greater. You know, you've got so many options. If it doesn't look like it's going to work out, though, for any of those, another option is you can call it f of x and then look if the derivative, you take f prime, is always less than 0 or greater than 0. So these are pretty much your options. So I'm looking here, a sub n is 7 minus 6 over n. Can I make some sort of nice inequality with a sub n minus 1? Let's see. What would a sub n minus 1 be? It would be 7 minus 6 over n plus 1. And you know what? I can just use an inequality pretty easily. So let me show you what one option is, okay? We know for sure n plus 1 is greater than n. Yes? Oh, good. That means 1 over n plus 1, 1 divided by something bigger, is smaller than 1 over n. That means 6 over n plus 1 is less than 6 over n. Good? I'm trying to get this to match a sub n plus 1, so I need to multiply by a negative on both sides. But do you guys remember when you multiply by a negative in an inequality, what happens? You flip the direction of the inequality. So I have negative 6 over n plus 1 is greater than negative 6 over n. And then if I add 7 to both sides, I've basically achieved my goal. So 7 minus 6 over n plus 1 is greater than 7 minus 6 over n. This is a sub n plus 1. I've shown that it's always greater than a sub n. Okay. What does that mean in terms of the sequence being monotonic? Well, if a sub n plus 1 is always greater than a sub n, that means the sequence is monotonic increasing. And that part of the problem is done. It then asked us to determine if it's bounded. Before I get there, if you were like hating on this inequality business, I totally get it. Let me show you another option. A sub n is 7 minus 6 over n. If you want to call that, say, consider a function of x, f of x, which is 7 minus 6 over x. Now, sequences are not differentiable, so that's why we have to redefine a function of x. And 7 minus 6 over x, that's 7 minus 6x to the negative first. Let's take the derivative. So f prime of x, derivative of 7 is 0. Derivative of negative 6x to the negative first would be 6x to the negative second, which is basically 6 over x squared. X squared is always positive. 6 is positive, so the derivative is positive. If f prime is positive, that tells me f of x is always increasing. Therefore, a sub n is increasing. Monotonic, if you want to throw that in for the people. Okay, so that's another option. My students like this because it's just very plug and chug, just crank it out. You know, the inequalities kind of make them nervous, but it's a good skill to learn. I don't know, depending on where your math career is going. So moving on, the next thing we have to address is determine whether or not the sequence is bounded, and then if it's bounded, justify by finding the upper and lower bounds. You got it. So we just showed that the sequence is monotonic increasing. That means every single term is bigger than the one before. And when you're trying to show if a sequence is bounded, you want to show that it has both a lower bound and an upper bound. So let's think. I can find the lower bound really easily because the sequence is monotonic increasing. So the lower bound would just be the first term of the sequence. That's a freebie. So the lower bound is just going to be a sub 1, and that would be 7 minus 6 over 1, which is 1. Boom. Okay, now how do I find out whether or not there's an upper bound? What I want to determine is, you know, I know these terms are going up, 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 right? Each one's bigger than the one before. But do they go up forever like this and approach infinity? Or do they level off? Is there some upper bound? How do I determine that? Well, I just take a limit as n goes to infinity. I want to know as n gets large, do these level off? Is the limit going to be a finite number? Or is the limit going to be positive infinity? That's the question. So what we're going to do is look at the limit as n approaches infinity of a sub n, which is 7 minus 6 over n. Oh, this limit's not bad. N gets really, really large. This is going to go to 0. So the limit is 7. So that means basically the sequence is trapped between 7 and 1. That's my upper bound. Woohoo! So when you can find an upper bound and a lower bound, that means the sequence, an, is bounded. And they didn't ask for this, but every monotonic bounded sequence is convergent. So this is another way that you could prove that a sequence converges, by showing it's monotonic and bounded. Okay, that's all that I'm going to cover on sequences. So if you need more in-depth review, I have determining the convergence and divergence of infinite sequences. I have like 2 videos on that, and then I also have exam review videos and whatnot, all linked in the description. Okay, next problem. Determine if the series converges or diverges. If the series converges, find its sum. This is a huge hint because we can't find the sum of an infinite series most of the time. We only can find the sum when it's geometric, telescoping, or a Maclaurin series. So I'm looking at this guy. I mean, this is gold, you guys, because it already is narrowing down, right? All your options. This is not geometric. This is not a Maclaurin series. That means it's telescoping. So what do we do when we have a telescoping series? First, we have to find an expression for S sub n, the nth partial sum. And remember, we have to redefine our index because we're stopping at n. A partial sum is not an infinite sum. It stops at n. So you need a new index of summation. Usually we use I. So we'll start at 1, go to n. And then similarly, make sure you redefine these guys to be i's as well. So this is going to be 1 over square root I plus 1 minus 1 over square root I plus 2. Good? Let me point out a few things. This is the nth partial sum. Stop at n, so that should be the upper limit right there. New index of summation. You could use k, but I is the most common. We're starting at 1. Start where this starts. This should match. And then you just redefine all the variables here in the expression to be i's instead of n's. Now we're going to list out the first few terms and the last few terms until we see a pattern for what cancels out and what remains of our telescope. So let's start with I equals 1. You'd have 1 over square root of 1 plus 1, which is 2, minus 1 over square root of 3. This is for I equals 1. Plus, keep going, I equals 2. This would be 1 over square root of 3 minus 1 over square root of 4. I equals 2. Already I can see, these guys are going to cancel, right? Let's just do a little bit more till you feel super confident. I equals 3. Now this is 1 over square root of 4 minus 1 over square root of 5. I feel pretty confident. How do you guys feel? Like, I don't need to keep listing out more. I can already tell, okay, these cancel out. These cancel out. This one will eventually cancel out should I write the next one, but I got to stop somewhere. So that's good. Okay, the only survivor is this 1 over rad 2. And then now let me do the last few. So this partial sum ends at n when I equals n. So I'm going to start at the end, work my way backwards. I'm going to substitute in n for I. I'm doing the very last term. 1 over rad n plus 1 minus 1 over rad n plus 2. So this is I equals n. And then, just so you know what's coming, let's do I equals n minus 1. That's what comes before n. So n minus 1 plus 1, that's just going to be n. So 1 over rad n minus 1 over rad n plus 1. And see, these are already going to cancel. Maybe we do one more. That would be for I equals n minus 2. Very good. So this would be 1 over rad n minus 1 minus 1 over rad n. So let's see what's canceling out. The 1 over rad n plus 1s, the 1 over rad n, and then I know if I kept going, this would have canceled as well. So the only one that didn't cancel at the end was negative 1 over rad n plus 2, and the only one that didn't cancel in the beginning was 1 over rad 2. I'm going to give you guys some very useful tips with telescoping series. Are you ready? However many don't cancel, however many survivors you have from the beginning, should be the same number of survivors that you have at the end. So like if I had one term not cancel out in the front, I should have one term not cancel out at the end. Other useful fact, I plus 1 and I plus 2. How far apart are these expressions? 1 apart. So you should have one survivor, one survivor. You get what I'm saying? If this was I plus 1 and I plus 3 and they're 2 apart, I'd have 2 survivors and 2 survivors. Okay. That's like a way to check that you're doing things on the right track. You know what I mean? And my teachers never told me that. I just noticed over the years. Here I am sharing pearls of wisdom with you. Okay, so this means S sub n is 1 over rad 2 minus 1 over rad n plus 2. What the heck do you do with S sub n once you have it? Well, you want to know, does it approach a finite number or not? So you take the limit as n goes to infinity. Sometimes this will go to infinity. Sometimes it goes to a number. Sometimes, I don't know, it'll go to negative infinity. Let's see. So as n gets really, really large, this is just a constant. This denominator will get large, so then this term just goes to 0, and we're going to be left with 1 over rad 2. And actually, since that is the limit of the partial sums, this is what the sum of the series is. How fancy. We have the sum, which means that the series converges. We didn't really use a test. This is just like definition of a convergent series based on the fact that it was telescoping. Okay? I think they're fun. They used to make me nervous, and then, once I practiced enough, I felt better about them. Now I love them, which is good because I'm surrounded by series in my life all the time. Okay, let's look at another one. Determine if the series converges or diverges. If the series converges, find its sum. So again, they're asking for the sum, which means it's either geometric, telescoping, or a Maclaurin. It doesn't look like it's any of those to me. So let's see. Don't forget about your test for divergence. What does the test for divergence say? If the limit as n approaches infinity of a sub n is not 0, then that means the sum n equals 1 to infinity of a sub n diverges. This is the test for divergence. It can only be used to prove what is in its name, the divergence of a series. Don't ever think about using it to prove a series converges. It cannot be used to do so. All we can say is, if the terms don't go to 0, then the sum of the terms diverges, okay? If the terms go to 0, we have no information. Pick another test. Test for divergence does not apply. It can only be used for divergence. Just remind yourself that. I'm making such a big deal because look, what is the limit as n approaches infinity of the natural log of 2 over n? Well, as n approaches infinity, this quantity is approaching 0. So if you imagine your natural log graph, when we approach 0 from the right, this is going to go to negative infinity. If you couldn't think of that right away, you could use your log properties to rewrite this as natural log of 2 minus natural log of n, right? That's another way. And then if n's going to infinity, natural log of n's going to infinity. This is just some constant minus infinity. So this limits negative infinity. So no matter how you slice or dice it, the terms a sub n are going to negative infinity. If you were able to remember the graph, let me just show it for those of you who are interested in the first thing I talked about. This is our graph of natural log of x, right? Very crude graph. But as the argument is approaching 0, it has to be from the right though. You see how the graph's going to negative infinity? So at this step, you could have just said negative infinity if you're really comfortable with the graph, okay? Regardless, if you get here one way or another, that's perfect because negative infinity is not 0. And what do I know? If the terms don't go to 0, if the limit of the terms is not 0, then the series diverges. So then this tells me that the sum, n equals 1 to infinity, natural log of 2 over n diverges, and I would say by the test for divergence, because that was what you used to make that conclusion. Okay? Good. Good. Okay, moving on. Use the root test to determine if the series converges or diverges. Fully justify each step. So they're telling us to apply the root test. You probably would have picked that anyways. So the root test tells us we take the limit as n approaches infinity of the nth root of the absolute value of a sub n. And then we compare that limit with 1. So let's see. The limit as n approaches infinity, I'm going to take the nth root of n over n to the 1 over n plus 6 raised to the n. Okay, now I can rewrite this. When I take the nth root of something, that's the same as raising it to the 1 over n. So the numerator is n to the 1 over n. And then the denominator, this n cancels with the n that's the exponent on this entire quantity. So then I just have n to the 1 over n plus 6. Good? Okay, now here we have to have a very serious discussion about this n to the 1 over n. Because as n approaches infinity, the base n is going to infinity, and the exponent is going to 0. And infinity to the 0 is an indeterminate form. It is. You can't just assume it's 1. Nope, so sorry, guys. So what do? What in the world do? You do a little aside moment. When you have an indeterminate power like this, you need to apply L'Hopital's rule. If you're rusty, I'll link a video in the description. But here's the dangerous part. L'Hopital's rule can only be applied to differentiable functions, and sequences are most definitely not differentiable. So what you have to do is consider some function of x. That way we can go ahead and apply L'Hopital's rule. And it kind of feels silly if you're looking at it from, strictly the standpoint of I'm just swapping out letters. But conceptually, it shows that you understand when you can apply certain calculus rules versus when you don't. So it has such deep meaning, okay? So don't take it lightly. Here's my aside moment so we can compute that limit, okay? I'm going to let f of x equal x to the 1 over x. So when you need to take the limit and it's an indeterminate power, and my goal is to eventually use L'Hopital's rule. Remember, L'Hopital's rule can only be applied when you have an indeterminate form of the type 0 over 0 or infinity over infinity. So I need to make some sort of fraction somehow. How do we do that? Well, we're going to take the natural log of both sides. So if y is equal to x to the 1 over x, ln of y equals ln of x to the 1 over x. And then using my log properties, I can move that in the front. And this is ln of x times 1 over x, which just becomes ln of x over x. Okay, so now let's take the limit as n approaches infinity of the natural log of y, which is the limit. Why did I say n? I meant x. Shame on me after that big speech. As x approaches infinity of natural log of x over x. Now, can I apply L'Hopital's rule to this limit? The numerator is going to infinity. The denominator is going to infinity. So yes, I can. And you should tell everybody that's what you're doing. So put L apostrophe H, or some instructors just put an H with a circle, whatever. Just let everybody know that's what's going on. So we've got the limit as x approaches infinity. Derivative of ln of x, 1 over x. And then derivative of x is just 1. So this is the limit as x approaches infinity of just 1 over x, which is going to give us 0. Okay, but remember that was the limit for the natural log of y, or the natural log of f of x. How do I figure out what the limit is of the original function? Well, what's the inverse operation or function for a natural log? It's an exponential function whose base is e. So this means the limit as x approaches infinity of just f of x is going to be e raised to the limit as x approaches infinity of ln of y. Because then basically you can just pull the ln out, right? Then you have e to the ln limit as x approaches infinity of y. And then we know what that limit was. This was all 0. So this is e to the 0, which is 1. Now, I don't make my students show all of this. Basically, I just tell them, when you get your limit, if you added an extra ln, then at the very end, you can just take e and raise it to that number. So basically, you can just say the limit as x approaches infinity of x to the 1 over x is e raised to the 0, which is 1. And just call it a day, okay? Boom. All right, so what do we do with that now? Well, we can conclude. Remember, we had originally the limit as n approaches infinity of n to the 1 over n. Well, that limit must be 1 also. So back to the problem that we had, it was right here. Let me see, do I have space? No, I have no space. I'll just squish it in here. We know that each of these approaches 1 now. So this limit is going to be 1 over 1 plus 6, which is 7. Well, what do I care about the fact that the limit's 1/7? When we're doing the root test, we always compare this limit to 1, and this is less than 1. So now I can summarize what's going on. So this means the sum, n equals 1 to infinity, n over n to the 1 over n plus 6 to the n, it converges by the root test. Okay, so I think the trickiest part of this problem was that limit that was an indeterminate form. Remembering you need to redefine it as a function of x, take the natural log, and then you can do L'Hopital's rule and put it back in. Oh yeah, okay. Here we go, here's another. Use the integral test to determine whether the series converges. You must still check the necessary conditions. Now, if they hadn't told me to use the integral test, you totally could have done like limit comparison with geometric or other things, all right? But since they specified which test, then we're gonna have to use it. But it's not that the integral test is the only test that would work on this series. If you wanna try it again, yeah, limit comparison with geometric would be really nice. Okay, so when we do integral test, again, we have to redefine the terms of our series as a function of x. So we're going to say, let's let f of x equal 3 over e to the x minus 1. And we still need to check the conditions that are necessary to be met before applying the integral test. And remember, there's 3 of them. The first one is we want to make sure f of x is continuous on whatever the limits of integration are. So it would be like 1 to infinity, matching the index of summation on the infinite series. So is f continuous on 1 to infinity? Well, all you need to do is really just identify the domain of the function. And as long as it doesn't have any discontinuities on this interval, you're good. So we would have a domain issue if the denominator was 0. The denominator is 0 if x is 0, right? Because then you'd have e to the 0, which is 1 minus 1. Okay, so the domain of my function is all real numbers or all x's such that x is not 0. But that's fine because 0 is not a part of the interval from 1 to infinity. So we're good. Is f continuous on 1 to infinity? Yes, that condition is satisfied. The next thing we need to check is f of x positive on the interval from 1 to infinity. This one you usually just do by inspection. You just look at it and you go, yeah. E to the first is 2 point blah, blah, blah. And that's going to be positive. And then all the terms after that, yep, this is just going to get bigger and bigger. They're all positive. You don't really do a whole lot. The last one is f of x decreasing. And if you can just look and tell, usually I put a check mark. If it's not obvious, then you have to take a derivative or do something like that. But I mean, as far as I'm concerned, this is pretty obvious. We know exponential functions are monotonic increasing. So if this is getting bigger, bigger, bigger always, then for sure 3 divided by something getting bigger is always getting smaller. So that one's obvious. I don't think you need to take a derivative to show it. I'll do another function later where it's like not obvious and we need to take a derivative, okay? All right, so then this means we are good to go. We can use the integral test. Okay, to use the integral test, even though they told us to. How rude if it didn't meet the conditions and they told us to. Okay, so what do you do now? You set up an improper integral whose limits match. The index of summation here is going from, n goes from 1 to infinity, so those need to be our limits of integration. Okay, 1 to infinity, and then we're going to integrate f of x. 3 over e to the x minus 1 dx. Okay, first things first, redefine the improper integral as a limit. So we're going to let this be the limit as t approaches infinity. Now integral goes from 1 to t 3 over e to the x minus 1 dx. Beautiful. Okay, this antiderivative is not super straightforward. We're going to do a u substitution. We sure are. So let's come in, let's let u equal e to the x. And then du would be e to the x dx. But you might be saying, Professor V, all I see is dx. I don't see e to the x dx. You're right. So let me just get this dx all by itself. So du over e to the x is dx. And no, I can't sub this out with du over e to the x. But remember, e to the x is just u. Oh, okay. So then that means dx is equal to du over u. Perfect. So I'll replace dx with this. And then 3 over e to the x minus 1 is going to be 3 over u minus 1. The only other thing we need to take care of is making sure we switch these limits of integration. So right now, these limits belong to the variable of the integral, which is x. I need to switch them to be limits for u. So I'm going to sub them in for x. They belong to x. So u of t is going to be e to the t. That's my new upper limit. And u of 1 is e to the first, so just e. How are we doing? Good? Okay, so now we have the limit. T goes to infinity. That part doesn't change. My limits of integration are going to go from e to the t. Then I have 3 over u minus 1. And then dx is du over u. You guys okay? Oh, good. Now from here, let's rewrite things a little more nicely so we can get an idea how we're going to do this integral. Okay, let's take the 3 out. And then we have e to the t, 1 over, watch how I'm going to write this, u times u minus 1 du. Are you inspired? Moderately inspired? Yes, we're going to do partial fractions for the integrand. We sure are. Okay, partial fraction time. You know, I want like a really light, gentle purple. That will make everybody happy. Can it be found? I don't think so. There was one that I liked. Let's try this guy. So partial fraction time. So both of the factors in the denominator are linear and they're not repeated. So we're just going to have, let me do it below the page break. It's going to bug me. 1 over u times u minus 1 equals a over u plus b over u minus 1. Then we're going to multiply by the LCD, which is u minus 1. So then I have 1 equals a times u minus 1 plus b times u. And then just solve for a and b. Let me let u equal 1. Then I have 1 equals a times 0 plus b. So b is 1. And then let me let u equal 0. Then 1 equals a times negative 1 plus b times 0. So a is negative 1. Good? I love it. So then now let's rewrite this integral using the decomposition. So we've got the limit. T goes to infinity. Limits are, oh, I forgot the 3 out there. Excuse me. 3. Yes. E to the t. And then I have a, which is negative 1 over u, plus b, which is 1 over u minus 1 du. Good? Okay. This antiderivative, we should be good to go. Each of the terms, limit t goes to infinity, just keep the 3 here. Antiderivative of negative 1 over u is going to be negative ln absolute value of u, plus, similarly, we'll have ln absolute value u minus 1. And this is going to get evaluated from e to the t. Okay, hang in there. Limit t goes to infinity 3 times negative natural log absolute value e to the t plus natural log absolute value e to the t minus 1, that's the upper limit, minus my lower limit, negative natural log, I don't need absolute value on e, it's already positive, plus ln, this is e minus 1. Okay, good. So let's see, let's clean up a little bit more. This is going to be the limit. T approaches infinity, keep that 3 out there. Now, I'm noticing here, as t goes to infinity, I know e to the t is going to infinity. I could simplify this, but I'm not going to. Hold on a second. Watch people. This term here is going to positive infinity. This one's going to negative infinity. And that's a problem because positive infinity minus infinity, which is the same as negative infinity plus infinity, that's an indeterminate form. But it's not such a big deal when you have these natural logs because we can use the natural log property and kind of fix the issue. So I have natural log. The positive argument goes in the numerator. So the argument from the positive natural log, goes in the numerator. So we have natural log absolute value e to the t minus 1 over e to the t. Did I lose you? This goes up here. Yeah? And then this goes down there because it was negative. Okay. Plus natural log of e is just 1 minus ln e minus 1. These are just constants, okay? So I'm not really worried what's happening as t goes to infinity. What's going on here? T is going to infinity. So this is infinity in the numerator. That's approaching infinity. This is approaching infinity in the denominator. You could apply L'Hopital's rule if you want off to the side, or you don't have to. So like a little baby aside, if we want to look at the limit as t approaches infinity of e to the t minus 1 over e to the t, you could do L'Hopital's rule, or you could just divide everybody by e to the t. So multiply by 1 over e to the t. And then what do we have here? The limit t approaches infinity. In the numerator, I'll have 1 minus 1 over e to the t, and then just a 1 in the denominator. So as t gets very, very large, e to the t is getting very, very large. We know that. So 1 over e to the t is going to 0. And then all I'm left with is 1 divided by 1, so that's 1. Perfect. So that tells me here, this whole argument is going to 1. Well, natural log of 1, that's going to approach 0 then. So my final limit is going to be 3 times 1 minus ln e minus 1. And you go, what do I care that's the value of my limit? How is this significant? Ask yourself, what test did I use? I did integral test. On integral test, we don't care like what the value of the limit is. All we care is that it's finite. So we're not comparing it to 1 or anything like that. All I care is that it's finite. And if it's finite, that tells me the improper integral converges, right? Just think when you first learned improper integrals, that's all you cared about. Improper integral converges, which then tells me that the sum n equals 1 to infinity 3 over e to the n minus 1 also converges by the integral test. Good? I always write what test I use because that's how my professor wanted all of the questions answered. So even when they ask you and they tell you what test to do, I still write it out of paranoia. Okay, how are we doing? Good. Next, determine the convergence or divergence of the series. So this time they didn't say what test to use. I'm going to let you pause the video and try it on your own and see if you could pick the right test. Did you try it on your own? Did you do test for divergence? I know, don't forget about that test. It's like everyone wants to jump into the more involved tests, but if you do a quick check, I go highest power of n in the numerator is 1. Highest power of n in the denominator is also 1 because you have square root of n squared. And then I look at the ratio, 6 divided by 2. That means the terms are approaching 3, which is not 0. So boom. Already in my head, I'm like, oh, test for divergence. This series diverges. So let's show it nicely. here we go. We're going to look at the limit as n approaches infinity, 6n plus 6 over square root 2n squared plus 3n plus 6. So in my head, I did like the pre-calc style shortcut to take the limit. Let's write it out nicely because probably on your exam, that's what you're going to need to do. So when we take this limit, I'm going to divide top and bottom by highest power of n from the denominator, which is not n squared. Since it's sitting underneath the radical, it's actually just n. Technically absolute value of n, but since n's going to positive infinity, we don't have to worry about the absolute value. So I'm going to multiply everybody by 1 over n. 1 over n. Now remember, when you put 1 over n underneath a radical, and it wasn't originally under a radical, it becomes 1 over n squared. So I'll write all that out for you. This we're going to distribute, so we're going to have 6 plus 6 over n, and then underneath the radical, don't forget, this is going to be 2n squared over n squared, you have to square it, plus 3n over n squared plus 6 over n squared. And then now let's simplify and take the limit. So we have limit, n goes to infinity, 6 plus 6 over n over square root 2 plus 3 over n plus 6 over n squared. And then from here, if n gets large, 6 over n goes to 0, so does 3 over n, so does 6 over n squared. And all that I'm left with is 6 over rad 2. You can rationalize it if you care. All I care is that it's not 0. So if the terms aren't even approaching 0, there's no way if I sit there and add them up, this series will converge or approach a finite number. So then just summarize your findings. That means the sum, n equals 1 to infinity, 6n plus 6 over square root 2n squared plus 3n plus 6 diverges by the test for divergence. So I know what you're going to ask. You're going to ask, so when should we use a test for divergence? Because that's what my students always ask me. And I'll tell you this, always. The minute someone gives me a series and I have to figure out if it's convergent or divergent, I do the test for divergence most of the time mentally, and most of the time it's inconclusive. Most of the time the terms will go to 0, and then the test for divergence doesn't apply. Remember, it can only be used to show a series diverges, and then I'll have to go through my list and pick something else. Integral test, limit comparison, alternating series, ratio test, blah, blah, blah. But always check test for divergence first, because if the series fails, right, if the terms don't go to 0, then you're done, and it was quick and easy. So mentally, I am always checking. Do I sit there and explicitly write out, I did test for divergence and it was inconclusive? No, because it gets boring and repetitive. But make sure you get in that habit. Just check always. Check, are they going to 0? Because if not, you're done, right? Fab. Okay. Determine if the series converges absolutely, converges, meaning converges conditionally, not absolutely. So this would be conditionally, or diverges, okay? So always test for absolute convergence first, unless it's obvious that the series diverges overall. If you need a video going over absolute versus conditional convergence, I have an amazing one. I'll link it in the description, and I even go through like an analogy to help you understand. So first we're going to test for absolute convergence. Okay, and in that case, we're going to look at the absolute value of a sub n, which basically all that's going to happen is that alternating part, the negative 1 to the n, goes away. So we have 1 over 5n to the 3/4 plus 4. So what do we think is going on with the sum, n equals 1 to infinity, of 1 over 5n to the 3/4 plus 4? I always look at what's the highest degree term in the numerator and denominator. And in this case, all I'm looking at is the fact that we have 1 over n to the 3/4, basically. Strip away all the extra. It's not going to do a whole lot when it comes to convergence or divergence. Well, what do I know about 1 over n to the 3/4? Nothing exciting, but I know the sum n equals 1 to infinity of 1 over n to the 3/4. That's a p series. P is 3/4, which is less than 1, which tells me this p series diverges. Make sure you write the sigma. Don't just write this by itself, because without the sigma, it's just a sequence. Okay, so here this is giving me p series vibes. P is 3/4. The 5 and the 4 aren't going to do a whole lot. So if this guy diverges, this will probably diverge as well. That being said, what should pop into your head is you're either going to do direct comparison or limit comparison test. We cannot use direct comparison. Why am I saying that? If you're trying to show your series diverges with direct comparison, you need to show that these terms are larger than the terms of some divergent series. They are not. They are a wee bit smaller. So since I cannot show the correct direction of the inequality that I need, we're going to do limit comparison, okay? And most of the time my students like limit comparison anyways because it works more often than direct comparison, right? So we're going to use limit comparison test. So in limit comparison test, we take the limit as n approaches infinity of the terms of our series. So that would be 1 over 5n to the 3/4 plus 4 over the terms of the series that we're comparing it to. So 1 over n to the 3/4. And then this guy's just going to flip up top. So we've got now limit n goes to infinity, n to the 3/4 over 5n to the 3/4 plus 4. Yes? Okay. This is going to go to infinity. So is this. I don't want to do L'Hopital's rule because I can't. This is with n. And if I were to, I'd have to redefine a function of x. I'm like not in the mood. So the easiest thing to do is just divide by the highest power of n, top and bottom. So divide by n to the 3/4. That's the same as just multiplying by 1 over n to the 3/4, okay? And then let's see, then we've got now limit n goes to infinity, 1 over 5 plus 4 over n to the 3/4. I know this is going to go to 0, so my limit is 1/5. What do I care about the limit when we do limit comparison test? I care about two things, that it's finite and not 0. I don't care about the value, if it's 100 or 1/5 or whatever. I just care that it's finite and not 0. And what does that tell me? All it tells me is that my series behaves the same as the one that I compared it to. So the number itself does not tell you whether it converges or diverges. Getting a non-zero finite number tells you what you compared your series to is how your series behaves. They behave the same. So this means my series, the sum, n equals 1 to infinity, of 1 over 5n to the 3/4 plus 4 also diverges by limit comparison test. Okay? Now you're probably wondering, well, what if we got infinity or 0? What do we do then for the limit comparison test? That's usually on you. That means you picked the wrong series to compare it to. So your limit comparison test is inconclusive if you get infinity or 0, and try again. Either pick a different test or pick something different to compare it to. So that's like a you problem, okay? If you get infinity or 0. Now, since this series diverges by limit comparison test, and that was the absolute value of my original series, then I can say, well, that means the OG, negative 1 to the n over 5n to the 3/4 plus 4, does not converge absolutely. All right. Am I done answering the question? No, because now I need to check, does it converge conditionally? I need more space. So let's address that. Does it converge conditionally? When you test for conditional convergence, you always use AST. Always and forever. Don't you love it? My students love it when I have an always statement for them. Use alternating series test. So for alternating series test, you look at B sub n. B sub n is basically the same thing as absolute value of A sub n. So just get rid of that alternating part. B sub n is 1 over 5n to the 3/4 plus 4. You know, I'm so sorry. That 1 is like aggressively large. Okay. We have to check two things about B sub n. First thing is B sub n decreasing? You can take a derivative if need be, but don't forget to redefine it as a function of x, or just use an inequality. And that's what I'm going to do. Because look, B sub n plus 1, which is 1 over 5 times n plus 1 to the 3/4 plus 4. If I compare that with just B sub n, I can for sure say it's smaller. For sure. Why am I so confident? Well, this denominator is bigger than this denominator. So if the denominator is bigger, then the whole fraction is smaller. Beautiful. Straightforward. Then the next thing I have to show is that the limit as n goes to infinity of B sub n is 0. Is that true? Let's take the limit as n goes to infinity, 1 over 5n to the 3/4 plus 4. Well, yeah, because this denominator is approaching infinity, constant over infinity, that goes to 0. Boom. So then that tells me, okay, the sum, n equals 1 to infinity, negative 1 to the n over 5n to the 3/4 plus 4, that converges by the alternating series test, which then tells me my original series, while we know it does not converge absolutely, I can say it converges conditionally. On the condition that it's alternating. On the condition that basically half the terms are negative. That helps it converge. Okay? If any of those concepts were not totally solid for you, then watch that extra video that I have on absolute versus conditional convergence, okay? Next one, and we're being asked the same question, if it converges absolutely, conditionally, or if it diverges. So we have the sum n equals 1 to infinity, negative 10 to the negative n. So always test for absolute first. Always test for absolute first, unless you can tell that it's going to just diverge, okay? So let me look at the absolute value of a sub n. Absolute value of negative 10 to the negative n. Now be careful. The negative exponent just means that you rewrite this as 1 over, negative 10 to the n. It doesn't go away though. But since I'm taking absolute value, then the negative in front of the 10, that does go away. So this is just 1 over 10 to the n. That's the absolute value of an. Well, you guys, what do we know about the sum n equals 1 to infinity of 1 over 10 to the n? You could rewrite it as 1/10 to the n, which is geometric. R is 1/10. And the absolute value of r for geometric, we always compare it with 1. If it's strictly less than 1, then that tells me this series converges, which means my original series, which had that negative in it, negative 10 to the negative n, it converges absolutely. And absolute convergence is the strongest type of convergence. It's stronger than conditional convergence. So I don't need to do AST. I'm actually done with the problem now. Isn't that beautiful? Look at us go. Okay, next one. Determine the convergence or divergence of the series. So in this case, they're not telling us what test to use. We're not doing absolute or conditional convergence. We're just testing for convergence or divergence. And the minute I see this negative 1 to the n, I'm thinking, let's do alternating series test, right? Because it's an alternating series. So b sub n is natural log of 5n plus 5 over 5n plus 4. We have two conditions to check. The first one is bn decreasing. And it's not super obvious if you look at the inequality. Bn plus 1 would be natural log 5 times n plus 1 plus 5 over 5 times n plus 1 plus 4. And I'm saying it's not super obvious if you try to compare this with b sub n, which one's bigger, because the numerator and denominator are both getting bigger a little bit. So who's to say overall which one's bigger or smaller? So I would say in this case, I would take the derivative just to be super safe. So I'd say let's let f of x equal natural log 5x plus 5 over 5x plus 4. And I'm going to take the derivative to try to see if it's decreasing. So when I take the derivative, I want to see if I can show that it's always negative, right? For a natural log, you don't have to take the derivative directly. Let's use our log properties so we can make life easier on ourselves. So I'll write this as natural log 5x plus 5 minus natural log 5x plus 4. Good? Okay, now let's take the derivative. So then f prime of x, remember derivative of ln something is 1 over the something, and then we have to do the chain rule, multiply by 5. So this will be 5 over 5x plus 5 minus, and then derivative of the next term would be 5 over 5x plus 4. Now you could say already this is negative because this denominator is bigger than this one. The numerators are the same. So this term has to be smaller than this one. So if I subtract something bigger, it's negative, right? So you could just be done. You could say this is negative. That's cool. If you didn't spot that though, then just get a common denominator. It's not a big deal. So common denominator would be 5x plus 4, 5x plus 5. And then if you clean up the numerator, you'll see that you're just left with a negative constant. So when I distribute here, this is going to be 25x plus 20 minus 25x minus 25 over the denominator. And then see how the 25x's cancel, and then you just have 20 minus 25. That's negative 5. And then I know in the denominator, we've got like 5x plus 4, 5x plus 5, you know, but x represents or will only take on the values that n takes on here from 1 to infinity. So I have no worry that this will be negative because we're only plugging in from 1 to infinity. And since I have a negative in the numerator, for sure this is less than 0. So at long last, we can say, all right, f is decreasing, which then means bn is decreasing. Hallelujah. Okay, one more condition for AST. Do you remember what it is? Yeah, you have to show that the limit as n approaches infinity of the terms is 0. So is the limit as n approaches infinity of natural log 5n plus 5 over 5n plus 4 0? Well, when n goes to infinity, both numerator and denominator go to infinity. I don't want to do L'Hopital's rule because remember, this is not a differentiable function. So you can take the ln out and just pass the limit through if you want. And then I'm going to divide everybody by the highest power of n in the denominator, which is n to the first. And then that should do the trick. So this is 5 plus 5 over n over 5 plus 4 over n, right? And then now as n gets large, these go to 0. And then I just have 5 over 5. That's 1. So this limit is natural log of 1, which is 0, which is the condition that we needed. So then this tells me the sum, n equals 1 to infinity, negative 1 to the n, natural log 5n plus 5 over 5n plus 4. This guy converges by alternating series test. Woohoo! All right, you guys, so we're pretty much a little bit past the halfway point on this exam. There were 20 questions.
I'm going to stop here. This is part 1. I'll finish it in another video. So make sure you're subscribed and you have your notifications on. That way you get notified the minute it's released. And like I said, in the meantime, if you just want to review other topics, then everything's linked in the description. You can also follow me on Instagram, TikTok, Twitter, Math with Professor V. I love you all so much. Thank you for your support. And I will be back sooner than later with part 2. So stay tuned. Bye.